Alright, hi everyone. Today we'll be talking about the diffraction grating, and here up at the top I'm just going to go through a small introduction, and then I'll switch to two videos of me recording the measurements that you'll be using in order to calculate the wavelength of the two laser beams that I'll be using in this experiment. So here, just to remind you again, this will be reiterated in the experiment videos and also seen, hopefully, the diffraction grating to the screen, which would be considered our ruler. In that particular experimental setup is 21.1 centimeters, and we would actually call this in our math equations capital L. Alright, and that should be the same regardless of which two laser beams we're looking at for that experiment. The type of diffraction grating that we'll be looking at as well, there are three of them in that little setup, but we're using the middle one, which has 300 lines per millimeter. Lastly, this would be our theoretical value that we're going to compare to, at least for the first experiment, so that we can gauge whether or not, by validating our sort of experiment and the explanation of diffraction gratings, we can then hopefully feel some confidence in terms of the value for the wavelength that we get for the green laser, which is unknown, and that unknown value can have some confidence if we get a fairly good percent difference from this from doing this experiment. So you'll need to sort of average over all of the values that you can possibly find. All right, so in practice, this is essentially how the diffraction grating would be set up. You'll have a diffraction grating with some incident light beam. In this case, it should be monochromatic, since it will hopefully only have one dot per an order. Unfortunately, I discovered that the green laser is actually dichromatic, so it will actually have two dots, but we'll look at only one of the dots, and I believe it will be the more inner dot that we'll look at for the green laser. The diffraction grating will diffract the light based on the wavelength and the size of the slits between each other, and will form a diffraction pattern based on this particular equation down here, where D is related to the number of lines or slits per unit length via this equation here. All right, and then there will be some angle, so non-linear component as to where those maxima will be seen on our screen based on the sine theta term. And that should be equal to the order in which we see them, so there will be various orders based on the central maxima location. Anything that deviates from the central maxima location will be first, second, third, fourth, so on and so forth, until you've reached the maximum orders possible for that particular wavelength of light, lambda. All right, so here in this setup, this single beam of light will be split into several beams, in which will appear on our screen as either dots or maxima in this case. And based on the fact of where we might know where our central maxima is located, we can then deduce what our first and second orders and third and so on and so forth. The pattern should be symmetric about the central maxima, so if we go down the screen in this order, it should go first, second, third, on and on, until you've reached your maximum amount. The ruler allows us to determine what this angle theta is so that we can then determine what sine theta is equal to. So in order to figure out what that theta is for each order, so theta 1 will correspond to first order maximum 1, theta 2 will correspond to second order M2, and so on. So each of these will have to be calculated separately for each of the types of orders that we see. All right, so to determine that, we need to know a little bit of trigonometry of our system, or geometry. In this case, we need to know the distance between the diffraction grating and our screen, which is our ruler, which I stated was 21.1 centimeters. And the next thing that you need to know is how much it deviates from the central maxima. So the ruler provides us with that information in centimeters as well. So you can determine what S1 is, basically the distance from the central maxima to the first order maxima, S2, which is the distance from the central maxima to the second order, and so on and so forth. So basically S1 will correspond to theta 1, S2 will correspond to theta 2, S3 to theta 3, and so on and so forth. Alright, so then to get that angle, you then need to employ some trigonometry in this case. So sine theta by definition is equal to the opposite height or side of our triangle divided by the hypotenuse, and our hypotenuse is found using Pythagorean's theorem. So a squared should equal b squared plus c squared, and our b and c are s and l respectively, and so we take the square root just to find the hypotenuse. Alright, so that can be found in terms of a decimal, and then just multiplied by d in order to then find what lambda is by dividing this quantity here by m. Now, one thing to note, when doing these problems, it's usually most helpful when you go and find what d is to make sure that you convert these numbers into the units of lambda. So if you're working in microns or micrometers, I would convert, or the wavelength is in microns or micrometers, I would turn d into microns or micrometers. Nanometers in this case for visible light, I would convert what you find d into nanometers, and I actually provide it down here, but I do recommend that you go through the process of figuring that out for yourself and verifying what it is that I got down here. The last thing that you'll need to do in this experiment is you'll need to watch the video, and as I'm kind of showing the measurements of where each of those are, make sure that you count the number of maxima that you see on one side of the central maxima itself. So what you'll need to do, say if there's a third one clear up here, and that's the last one that I show in the video, you would count 1, 2, 3, and that would be the total number of, or that would be the maximum order that you can see for that particular wavelength of light with this particular diffraction grating. So that's how you will determine it experimentally, and then theoretically, theoretically you would determine it in this manner here. And then you always need to make sure that you round down. Always do this no matter what the value that you get from this ratio here. If it's 3.99, it rounds completely down to 3, and so on and so forth. Alright, so in this example here with the red laser is 633 nanometers, and the diffraction grating should have a spacing of 3,333 nanometers. So if we do the ratio of those two numbers, we get 5.27, round down, so then our theoretical value should be 5 for that case. You'll need to do this for green as well, and it should be different based on the value of the wavelength that you get. And hopefully you will see more because the wavelength is smaller for green, which makes this ratio bigger. And so hopefully you'll see more dots from this diffraction grating in the green wavelengths. Alright, so here I just say that in this example the maximum number of orders we expect to see at this wavelength is 5 orders on either side of the central maxima. So just be aware of that. I'm not asking for the total number of maxima that we see, just the max order that we can possibly see off to one side. So just be aware of that. The total number of maxima would just be the max order times 2 plus 1, just as an FYI. But in this case, we're just looking for max orders in both cases. And you only need to calculate this once since there's only one wavelength for each of these lights. You'll need to do it for the red and the green, sorry, but you'll need to do it once for each laser. Whereas with this, you'll need to find the wavelength multiple times for the various S's in the experiment itself, and then average over the wavelength, and then find an average wavelength and compare to the value that I provided up above. Now with the green, you're just going to find the average wavelength, and hopefully with some confidence that we found in the red laser, we can then determine whether or not it is of acceptable value. And you can go and look up in sort of a diagram or a table what the general range of green light is and see whether or not it falls into that range, just for added confidence in that evaluation. All right, so then I'm going to cut to the experimental videos, and there you'll just write down the information. Okay, so here we have a setup of diffraction grating with a red laser. The red laser itself has a wavelength of 633 nanometers. The diffraction grating that we'll be looking at has an N value of 300 lines per millimeter. And hopefully you see the nice diffraction pattern that's created when we pass the laser beam through. So we will get the data for each of the maxima that we see on our diffraction pattern, like such. Okay, and this middle one here is our central maximum, so anything that deviates off that central maxima will be an order greater than 0. Sorry that the red lettering is a little difficult to see. That first maxima you see there is approximately at 4 millimeters, or 4 centimeters, sorry. The other one is in between the 8 and the 9. The third one is approximately close to 14. And the last one here, about 23 to 24, so somewhere in that region. So hopefully I can get it focused. Camera's doing all sorts of fun things. And that is the red laser. Next I'll show the green laser, and from that you'll have to figure out what the wavelength of that laser is based on the information that I've provided with this lab. Here we have the green laser set up in pretty much the same sort of position and configuration as the red laser with the same diffraction grating that we've been using, 300 lines per millimeter. Here we see most of the diffraction pattern. I'm going to have a friend of mine help me to show that some of this is actually leaking off the ruler. However, the only thing that we would care about with that is counting the number of maximum orders. For all intents and purposes, we have pretty much a good set of orders in order to try and calculate the wavelength of the green laser. You'll probably also notice that there seems to be 2 dots associated with each maximum. And this has to do with the fact that apparently this laser has 2 different wavelengths of green. So it's not fully monochromatic due to it possibly being a diode laser instead of a helium neon laser. So what we'll do for this is just choose the inside one, so the one to your left. Just read off that particular value on this side. That one looks a little bit more blobby. I'll try and estimate that value as best you can. For some odd reason, the first order on this side of the ruler seems to be more dominant. It's not actually the maximum, central maximum, but for some reason the diffraction grating does that. Here we have the central maximum there on the thick line with the circle on it. Now that we're using a green laser, the red numbers seem to appear much nicer, and on this side of the ruler what we'll use is the rightmost dot for each of the maximum. Oops, sorry. So there, that one's close to 7. Losing focus. That one's up more close, that dot's probably closer to 11 centimeters. And this last dot, I'm going to zoom in, it's around 17, somewhere around there. Alright, so we got 4 maximum shown on each side of the central maximum, with the 5th one that was off to the side. So when you calculate the max orders, just remember that there's that extra 5th one off to the side. All right.